Hi guys, this is the second half of the Unit 3 test solutions. I'm on number 6B, and for this one, it wasn't a very common choice, but I think that it's good to kind of see this technique that we want to find the point on this line that's closest to point P. So I'm going to call a general point P1 on the line that's given, and I'm going to say that P1 is going to be 2 plus 3t, so this is just looking at the parametric form, 1 minus t, and negative 4 plus t. Now, I would know, say for instance, if I had this line here, my line L, and I've got this point P out here, I know that the closest point is going to be perpendicular to the line. So I want to pick this point here for my P1 where I get that 90-degree angle. And what do I know about 90-degree angles with vectors? Well, we know that the direction vector of the line, M, which would be that 3, -1, 1, would have a dot product of the vector here that would equal 0. So we know that P1, that vector dot M, would equal 0. So that's what I'm going to do. Whoops. What vector P1 is. So I'm basically taking vector P1 and subtracting the components of P, and I don't want to run out of space here, so I'm going to kind of, well, I'll be okay for space, I think. 2 plus 3t minus 5, and then I have 1 minus t plus 2, because it's minus -2, and then negative 4 plus t minus 8. So this vector here is negative 3 plus 3t, 3 minus t, and negative 12 plus t. So once you get to that point, then I'm going to use that dot product, then do the dot product of that with the direction vector that will give me 0. So P1 dot M equals 0. So I've got this negative 3 plus 3t, 3 minus t, and negative 12 plus t dot with the direction vector 3, -1, 1 equals 0. So I get 3 times negative 3 plus 3t minus 1 times 3 minus t plus 1 times negative 12 plus t, and I am going to run a little bit short on space here. That's okay, we'll squeeze it in. Negative 9 plus 9t minus 3 plus t minus 12 plus t equals 0. And I hope we can all just believe me from there that t equals 24 over 11. So we're going to sub this in to two important different spots. So first, to get the point, if we sub t equals 24 over 11, then point P1, the point that I'm looking for here, equals, and I hope that you guys will just trust me here on the math, that you just substitute in that t value and work out each component. It's 94 over 11, negative 13 over 11, and negative 20 over 11. Then from there also, I'm going to put this into the vector P1 and find the magnitude. So vector P1 ends up, so we're subbing t equals 24 over 11 also into the vector, and then we get 39 over 11, 9 over 11, and negative 108 over 11. And then the magnitude of P1, we're just going to use the magnitude formula, the square root of 39 over 11 squared plus 9 over 11 squared plus negative 108 over 11 all squared. And that ends up being square root of 13,266, I think, over 11. And the square root squared with the 11 on the denominator ends up canceling out. So that's the distance, is that. And the point that gives that closest distance is the one there. So you can see I didn't even use the distance formula. This is kind of where that distance formula comes from. And to be honest, I don't memorize the distance formula. I just kind of use this technique knowing that I would have to go at a perpendicular, and that means that the dot product is 0. So here, give equations of two planes whose line of intersection is on the YZ plane. Your equations can be left in any form. So for this one, I had a lot of unique solutions for this, but I think what I was thinking you guys would do, some people came up with some very creative processes here. What I was thinking that you guys would do was to come up with that line of intersection. So if we know the line of intersection, that's going to be on the YZ plane. So both the component of the position and the direction vector would have x equal to 0. So I personally, when I was doing this, I just said, okay, my line of intersection is going to be any point on the YZ plane plus any direction vector that stays flat on the YZ plane. And the only thing I have to have is a 0 and a 0. The x and y components of both the position and the direction vectors can be anything you want. Anything. So you could put like 1, 2, 3, 4. Doesn't matter. You can have any values in there for your position vector. It can be any point that's on that YZ plane. And then any direction vector that keeps that line on your YZ plane. And then if I wanted the equations of two planes, remember that we would have the equation of, say, this plane. We could use the let's color code these maybe. We'll use the position vector here and the direction vector that's along the line. That's one of them, right? And then I might choose a different direction vector that's along this plane. So I've got my position and direction vector from the line, and then I just need another direction vector that would be on that plane. And I don't want to make it on the YZ plane. That's one thing a few people gave me, two different equations for the YZ plane. Well, they're not really intersecting on the YZ plane, are they? You've got a thing with infinite intersections. So I'm going to add an S and then any other vector, anything that's not collinear with these ones or not coplanar. We don't want to have two different equations for the YZ plane because they're not really intersecting there. But we want to have a line of intersection. So it could be -1, 2, 4. Any letters there. And S and T are any real numbers. And then plane 2 is going to be the same. So this would be like that kind of color coordinate here, that would be like that vector. And then there would be some other vector that would be along, let's see if I can draw it so it's on like, maybe draw it on like this plane here. That would be on the second plane. And that's just some other vector that's not necessarily on, and likely not at all, on that YZ plane. And you just throw in any other vector. So the trick was getting a line of intersection here, and then like that. S and T are any real numbers. And you could leave it in vector form. You didn't have to change it to any other form. Okay. The next one, this one there was a little bit more calculations and there was an exact answer. So for number 8, it said, given points A and B, so let's just throw those out there. A is 1, 2, 0, and B is 3, 1, 1. And then we've got point C that's on a given line and point D. Oops. So one thing here that was important was that when we're labeling these points is that they, in this order, A, B, C, D, form a parallelogram. That means I have to connect them in that order, A to B, B to C, C to D. That's what makes my parallelogram. Now, I'm going to write point C using the parametric form of the line that it's on. So the C would be 2 minus T, 2 plus T, and 5 plus 2T. And then D, kind of similarly, using the line that it's on, would be 7 minus 2S, 2 minus S, and 4 minus 3S. So that's a good start. Now, what I know about a parallelogram is that the sides are equal length and parallel. So we could say that those vectors would be equal. And the vectors I chose to look at, there are different ways of doing this, but I looked at vector BC and I looked at vector AD, and I said that those two vectors would be the same. So I'm going to find vector AD here. So remember, you're doing the end minus the start. So you have 7 minus 2S minus 1, 2 minus S minus 2, and 4 minus 3S minus 0. And that simplifies to 6 minus 2S, just negative S, which is kind of handy, and 4 minus 3S. And kind of similarly, I'm going to go in and do vector BC would be 2 minus T minus 3, 2 plus T minus 1, and 5 plus 2T minus 1. And that will simplify to negative 1 minus T, and 1 plus T, and 4 plus 2T. So if we know that these two vectors have to be equal, we know that their x and y and z components have to be equal, and that can help us solve for s and for t. So I know that BC equals AD. So I'm going to set up a system of equations here. I'm going to use the x components and the y components. So negative 1 minus T equals 6 minus 2S, and 1 plus T, actually I'm going to write this underneath, 1 plus T equals negative S. And this is actually set up it's not ideal for elimination, but I hope you guys can see, or you could rearrange this a different way. I'm just going to add this down and work out how to solve for S here. So elimination, normally we say get all of the X's in one row and or column and all of the Y's and all of the numbers, but as long as you pay attention to like terms, you're actually okay. So I'm going to say, look, negative 1 plus 1 is 0, and negative T plus T is 0. So that's great. That's 0 equals, and here I've got just a 6, so that'll go down there. And then negative 2S minus S, adding down. So I have 6 minus 3S. So then 3S equals 6 and S equals 2. So now I'm going to sub that back in to figure out what my T value would be. I'll probably use that second equation. So 1 plus T equals negative 2 because it's negative S. I I said 1 plus t and I wrote 1 plus 2. So t equals negative 2 minus 1, t equals negative 3. So that gives me what those values would be. I'm going to actually check the z's just to double check. It's always a good idea to make sure. So z equals 4 plus 2t, which would be 4 plus 2 times negative 3, which would be 4 minus 6, or negative 2. And then I'll do the other z. Z equals 4 minus 3s. So 4 minus 3 times 2, which is negative 2 also. So that's good news. So now I can just find point C and D by substituting in the S and the T values. So point C is going to be 2 minus negative 3, 2 plus negative 3, and I can write small enough in here, 5 plus 2 times negative 3, getting kind of squished, but that's okay. So then we get point C is 5, negative 1, negative 1. And then same kind of idea for D. D is going to be 7 minus 2 times 2, and then 2 minus 2, and 4 minus 3 times 2. And here we've got 3, 0, and negative 2. So those are the 2 points we've got there. And that's my C answer, and there's D. And the last one. So here we want to do 2 parts, and for part A, we want to create scalar equations for 3 planes given this criteria. If the normals are not collinear, so this means that none of the planes are parallel, but they are coplanar. Remember, coplanar meant that n1 dot n2 cross n3 equaled 0, and that meant that all of the normals would lie flat on a plane, and that this would be case 6 or 7. So either where they intersect in a line or they don't intersect at all. So this is honestly, I would choose, there's really truly an infinite number of possible solutions here. I would choose n2 and n3. Then I would do the cross product. And then I would figure out an n1 value where the dot product of that with the cross product equals 0. So you're going to use the answer from your cross product equals 0. So that will go back and be kind of similar to that previous question, question number 4, where you had to find things that would be perpendicular. So where the dot direction vectors where the dot product would equal 0 with the normal, similar to question number 4. Okay, so you can pick any 2 normal vectors for n2 and n3. Do the cross product first. Don't try and make the cross product equal to 0. That's really hard. But the dot product equaling to 0 is pretty easy. So whatever you get for your cross product, just find x, y, z components for your n1 that would make that new dot product equal to 0. Okay. For B, it's kind of the opposite. You want n1 dot n2 cross n3 that is not equal to 0. So here you can, this is honestly like the much more likely case to happen. So you can almost choose any 3 and just confirm. So I would again choose N2 and N3, find the cross product, and then find N1 so that N1 dot with your answer to the cross product is not 0, which it's easy to make it not 0 because it can be anything else. And none of the D values in the Cartesian equation matter at all. So you can pick any number in the world that you want for those D values. It does not matter. One thing that you just have to be careful of is that these guys are not collinear. That, again, because that would be parallel or coincident planes. But as long as you get two normals that are not collinear, do their cross product, and then you choose the third normal, either so that it would equal 0 when you dot product with the cross product answer, or so that it would not equal 0. And just knowing that that's case 6 or 7, and this one would be case 8. And that's it for solutions. Email me if you have any questions, guys.